Well, hello everybody and welcome to the next lecture in the course. Let's see if I can give you a little introduction here to Labview virtual instruments for implementing machine vision. So, a brief introduction to this then. As you know, Labview stands for Laboratory Virtual Instrumentation. I think it was developed in the 70s in California. And it lets you create programs with graphics instead of text code, as you know. And it makes it very different from what you might have been familiar to in the past, like C, C++, Java, or BASIC, probably all of us used in the past. But it allows you to perform many functions, but with requiring less time for programming and less experience of programming than traditional languages. All this programming aspects you have to deal with in languages like C, such as pointers and stack and other type esoteric structures in C, are all taken care of in the system. It doesn't you don't have to worry about the operation of the computer, you just worry about your algorithms and how you're going to record data. It was originally developed for instrumentation, for sort of data log in the field and so on. What can you do with Labview? Well, capture and process camera images for monitoring industrial processes, so surface inspection. We've been doing this for a long time. For example, many of the rigs we built, such as the aggregate analysis and the photo face, with the face analysis, was originally built using Labview. Labview is very good for getting cameras working together and for synchronizing laser lights going on and off with cameras. It's not so much designed for in-depth analysis. Okay, that'd be more like maybe MATLAB for that, stuff like neural networks and so on. But the thing is, Labview is pretty good because it comes with a VI which allows you to run a MATLAB script, which is kind of useful because you might want to run a script which is running, say, a neural network. You wouldn't try to code it in Labview. You just send the data to the MATLAB script, run it there, and send the data back to Labview again. And we've used that in the lab actually. Gary Atkinson, who's originally built the photo face rig in 2007. He did some of that for some analysis in that project we had at that time. Another thing it's typically used for is analyzing and processing electric signals. That's a very common thing. So it's waveform analysis, and there's a whole set of tools for that. Monitoring and controlling water levels. So I don't know if you've ever been to sort of canals, or we've got a lot of reens here in Somerset, and they have what look like ultrasonic or maybe more like infrared sensors pointing downwards at the water, and a little box, wires going into a little box. And what they're usually doing is monitoring the height of the water level so they can control sluice gates automatically and so on. And that would be the kind of thing you might use Labview for, because you might have a solar panel for getting electricity. You wouldn't need a great deal of power just for that. And then your data logging, you're analysing conditions, especially if you've got a lot of flooding going on, something like that. It's pretty important. Vibration analysis. It's the sort of thing where you could have a machine tool with little sensors mounted on it all over it, and you could be measuring the vibration during different types of cutting operations, for example. Another example we've got down here is evaluating stress and strain. So what we could do with that would be, we have strain gauges. I don't know if anybody has a great deal of experience of using strain gauges, but they're little very sensitive pieces of material which you mount onto objects. And then as the object undergoes strain, when the stress is applied to it, or a force, then you can measure the strain. Actually, I've got a little example in this presentation of that being used. And that is used very commonly in things like evaluating finite element models, because you can do a load of finite element modeling. There's no guarantees that the models you've got are actually valid. So what engineers tend to do is build a model, mount lots of strain gauges on it, and apply certain forces, and see whether the strains they're getting are kind of in line with what the finite element analysis they're running is telling them. And if it is, then that's kind of validated their models. Otherwise, there's a danger of producing phony data, which you have a lot of faith in, but there's not really any validity to. Now, there's a lot more on, perhaps worth having a look on the NI website, ni.com. It's worth having a look at that. So, carrying on down then, Labview's graphical programming language is called G. since it utilizes graphics that look like real instruments for the program inputs and outputs. Now, we talked about this before. You have your front panel with your controls and your indicators mounted on it. These correspond to icons that appear in the block diagram, which is where the code is really located. And then we can create connections between the icons which data runs along, and that's how we control the operation of the program. Now, we can create sub-VIs, which are like subroutines. We do that, of course, in regular programming. And we can do that also in Labview. We can just create a little subroutine like this little simple operation and save it and then insert it wherever we want. And that bit of processing will be taken care of by the other operation. Another thing you can do actually is you can have a larger Labview G code program in your block diagram, and then you can select part of it and turn it into a sub-VI that way. But I wouldn't really recommend doing that, not for what we're doing, because I would say it's easier, especially at this level, to just create your own little sub-VI. You've got full control, you know what's going on, there's no need to make things complicated really. Now, an actual Labview program that you create is called a VI, which stands for Virtual Instrument. So these little programs are built into your Labview code, and the reason they're called virtual instruments is because they can really imitate real-world instruments. So this chap, he's doing some tests with some electronics, no doubt, and this is a typical example of a real-world instrument. It might be some kind of elaborate multimeter. And you can connect your leads into the multimeter and measure voltages, currents, resistances, and so on, of course. But what you can do, I mean, basically in Labview, you can do the same thing. So you just have a suitable card inserted in your PC, and then you run wires on the card, and they're like your terminals going to your multimeter, and then you have a virtual multimeter in terms of the front panel that could be made to very closely resemble the real multimeter, but it's not a real instrument, it's a virtual instrument. And of course, the reason why scientists love and engineers love this so much is that they don't want to have a laboratory full of hundreds of real instruments taking up loads of room. They'd rather have just one PC where they can just run different programs and do all sorts of different kinds of instrumentation work. So that's the great boon of VI, and that's really where it came from, the whole idea, I guess. So this is an example of that. What we got here is replacing an actual instrument, this multimeter here, with this virtual one. Of course, we don't have to spend loads of money either on buying all this expensive instrumentation. We just buy one program, one computer and a card, and then we've got all this flexibility. Another reason why engineers and scientists love it again is that they can make it exactly as they want. They can customize it exactly according to what their needs are. For example, if they've got a physicist has an elaborate laboratory doing some experiments with lasers or whatever, he may not need your standard multimeter. He may need some frequency analyzer device, which is rather expensive to buy. And if he makes one himself, he can always modify it to do exactly what he needs in his particular application. And he can automate it to run by itself in various ways. So there's all sorts of flexibility that comes with having the instrument built using general purpose software such as Labview. And as we talked about before, Labview, you can simulate controls, such as sliders and dials. You can move the dial around with the move control. Types of switches, you put LEDs on there if you want, or indicators, like a thermometer. Waveform graphs, you can display readouts on the screen. You could simulate a cathode ray oscilloscope quite easily and generate a virtual CRO. And that would be a lot of an interesting project and traditionally quite an expensive instrument, so quite useful. Interactive input and output terminals of the VI is what we're talking about then, of course. All sorts of different ways of configuring them, and some people like configuring things more aesthetically than some people spend a lot of time on designing things. This is quite a good input because nice clear reading, and you can have these little buttons here to move things up and down. Sometimes a meter gives a clearer, immediate, quick glance at what's going on. I think that's why in cars you still have meters on the dashboard rather than digital readouts, isn't it really? And So controls, as I say, can simulate instrument input devices and supply data to the plot diagram, the VI. Indicators simulate instrument output devices and display data to the plot diagram. Display the data the plot diagram acquires or generates. And of course, you can change these entities between just by right-clicking on them. You can turn them from controls to indicators and vice versa. And as we saw, and as it shows here, as we said before, controls and indicators have represented in the block diagram slightly differently. The control has more of a solid outline, the indicator has more of a sort of hollow outline. And so we can take input data directly from the user through virtual instrument user interface, or from image capture or measurements of the real world. Now that's where you do need a card, of course, for the latter. But they're not that expensive. And one good thing about National Instruments is that they supply a vast array of cards, which accommodate just about everybody's instrumentation and needs, really. One type of card mentioned here we used to use a lot in Vision over the years was a frame grabber, which you install in your PC. And of course, nowadays you may not need a frame grabber, because you used to have to mess around with frame grabbers when we had these analog TV standards. And nowadays, we don't. We generally go for digital cameras, and we don't necessarily need any interface. We can just plug in a USB 3 or a Gig E, or even a FireWire if you want, I suppose. That's a bit out of date now. But the point is, you don't need a frame grabber. The only people who might retain the use of them would be people using Camera Link, which is a high specification way of interfacing a camera, so very high frame rates. You might have to spend about £1,400 on a frame grabber for that. But then again, if you're doing that kind of high spec work, probably you can afford that, because it's, if you're do very demanding visualization, vision capture, you've got to spend some money on it really, because very high speed cameras alone are generally very expensive. I mean, cameras that we use a lot of the time in the lab are typically a few £100s. I mean, they come down a lot in price. You can buy a perfectly good camera for about £500. We typically spend a few £100s on a lens as well, because there's not much point in a top of the range camera and a sort of second-rate lens. You want to get a lens which is matched to the camera. So if you've got a camera capable of megapixel, so 5 megapixel resolution, then you want to make sure the lens is also a megapixel lens. And camera suppliers and equipment suppliers like Stemmer Imaging and the guys will generally will give you a lot of advice on exactly what sort of camera lens combinations are good at for particular types of tasks, really. We buy a lot of equipment, so they're always talking to us about these things. And as it says there, the library of image processing VIs built in to Labview is known as the iMac software. Now, we bought Labview originally, what was it, in '99? And I remember buying all the Labview, and then we also bought something called Lab Windows CVI, which I mentioned before, which is a version of Labview, but it has C code rather than G code. So it's sort of a bit more like C. It's really a sort of National Instruments version of C for Labview. It's not quite as well supported, to be honest, as Labview itself. Labview is their flagship product, but it's still quite useful for some, especially for people who prefer to work in C. But then we bought Labview. I bought Lab Windows. Then we had to buy the iMac tools for Vision, this is also only £1,000. And then I had to buy the iMac tools for Lab Windows CVI, because it was all separate. They want to charge us for all of it. But one good thing though is if you're a university, you do get a big educational discount compared to what companies would be charged for this kind of software. As it says there, data is inputted from the real world. Usually requires data acquisition, DAC hardware such as the input-output card, taking analog voltages or digital data from transducers, or from the camera, of course, directly inputs it into Labview VI. Example of another example of the front panel there. Now, the input could be a switch, as it says here, that detects the presence of a part on a conveyor, thereby triggering acquisition of an image. And this would be a typical and very common machine vision application. So you'd have a conveyor belt, perhaps, where you'd have objects coming along it. Maybe, for example, a good application, I think, for machine vision is something like trying to detect glass fragments in the bottom of jars of honey. Very boring, very, very boring task, but pretty serious if they miss any and they only are there. You know. So when the honey jar comes along, it would break a light beam, say, and that would act as a trigger, which is also the image frame grabber, if it's got one, would have all these, in fact, all these cards have got trigger inputs, so it's got TTL logic input. So the switch input triggers the acquisition of an image. So you know that image is going to be captured exactly at the right time. And the card can also measure quantities such as temperature, anything, you know, analog inputs, speed, acceleration, pressure. As long as you've got a transducer, it can produce a voltage in relation to the parameter you're trying to measure, then you should be okay doing these measurements, really. And flow meters, accelerometers, so strain gauges mentioned again. And this is the example of the strain gauge I was talking about with what we got here. I don't know if you can see it on that diagram, but there's a little strain gauge. It's a very sensitive piece of material that varies in resistance according to the stress or the strain that it undergoes. So as this sort of hand exerciser is being operated, the strain will occur in this big spring here, and this will be measured in terms of the voltage change across here with this little circuit here to help get a decent response. And then we'll have an input to the NI from the output from this bit of circuitry. That's the idea of that. I remember seeing that one operating. And then once you've got your data, of course, you can analyze it, process it, and get the outputs or display the results. We can save on a file, quite often save it to an Excel file because our data, a lot of the time, people want it in a standard format so they can analyze it. And the kind of thing we were doing one time, for example, that Abdul was working on was he did his PhD in a system which was looking at tiles. So tiles were coming along a production line. I mean, quite a lot of tiles are made in the UK, Pilkington and other companies. There was a company down in Newton Abbot actually I went to, and they were getting a lot of scrap production, so it was quite a good application for tile inspection, but they were getting defects, and they really wanted to know, they wanted, the ideal situation would be for them to get all the data coming from the cameras, to be able to work out which part of the operation it was related to. For example, was it a forming defect for the tile, or was it a print problem? And then to address the relevant part of the production process. At the moment, you probably do that manually, but ideally, the long-term solution would be to be able to recognize the kind of error you've got and work out automatically what corrections needed to give you the right kind of product you're looking for. So that's called adaptive control. That's kind of a research aim, really, for a lot of work that's going on. So you recognize certain features, you realize the problem, the system estimates a correction, and then through actuators on the machinery, hopefully, it could actually correct the process to eliminate the error. That's the sort of dream that you have a lot of the time, these things. Now, if you have any luck on this, see if we can get you over this. This is a little example. Here we go. Hand dynamometer using the strain gauges. This is a little example. So here we go then. The strain gauge is operating. It's going into Labview. It's going through, this is a front panel on Labview, which is getting an analog readout of microstrains, and this can be calibrated. You can also read out the voltage there. So that's quite a good just example application there of the kind of things we can do with Labview. Another robotics application, and also involving vision, is this one here. So you can use Labview for taking the image analysis for process modeling and control, and use outputs from an I/O card to drive controls to influence the external environment, of course. So this could be used in manufacturing or inspection to check outputs and take corrective action as need be. This is a little simple example here. Labview with a robot, and a camera is identifying the location and type of the object, and the program is converting it to coordinates for the robot to manipulate the object. So if we can see this. This is dealing with a certain amount of uncertainty in the environment. The object's being thrown to different locations, and the robot is still able to correct its operation. A nice little demonstration there of the kind of things you can do with So going back to the Labview. So that's a little introduction to what's going on with VIs for vision, really. What I'd like to do is introduce, I've just saved this onto Blackboard, this document which is published by National Instruments, iMac Vision for Labview. So it gives quite a lot of interesting background on what we're talking about here. So if I just go on down, you can have this, you can read through this yourself at your leisure. I just want to introduce a few interesting things. Now it's worth reading through here because all this contents is pretty self-explanatory. We go on here to some background on where we're coming from with Labview VIs for vision. So it's telling you about the convention they're using the book. Vision Assistant. These are documents. In fact, you've got, of course, this is the one you've been working through in the tutorial. You can find these documents online. So background. So introduction to iMac Vision. And this chapter is given a nice little introduction to what we've been talking about on this course and where we're coming from with this machine vision, computer vision. And the controls palette, this is general background there. The controls palette, I talked about previously. And these are showing the icons that are available. Functions palette. So when it comes to operating with images with iMac, there are certain types of functions or VIs that do certain very useful things which you'll find useful for the assignment. Vision utilities, you manipulate and display images, for example. Image management. So you might remember I talked about iMac Create, where you get some memory available for the image in the computer. But every time you create it, you've got to dispose of it. You've got to use iMac Dispose. That's an example of image management. Files where you can read images and files. That's one of the first things we'll do in one of the upcoming weeks with Abdul, is that you'll read an image from a file, and then you can this will be a basis for the assignment, because I think if you've got something very simple like that, you can start building on it. You know, you read this image in, you process it, and then you can do all sorts of things as is needed for the assignment. It's a little file display. A part of that, of course, once you've read it into the computer, is actually to display the image, and this is a thing called WinDraw, which is what we got here. And there's a whole bunch of VIs that are designed for creating these windows for displaying images. There's all sorts of parameters associated with that. Now, there are various things you can do. Create regions of interest and do processing within the region. Another one here is image manipulation. And it's worth just getting these out, running Labview, getting these VIs out, putting them on the screen, on the block diagram, putting on context help again, and then going through, seeing exactly what we got. Pixel manipulation. This is where you can read and modify individual pixels in an image. For example, you could, these VIs are great. They're really powerful, they're really optimized, but sometimes in research they don't do exactly what you want. So sometimes it might be necessary to use one of these pixel manipulation VIs to read the pixel values out of an image into an array and start manipulating it, doing specialized processing that you want to do as part of your in-depth analysis. This is all fairly self-explanatory. Overlay, calibration. Calibration is a big part of machine vision, of course, because when you've got your image, you've got to relate it to the real world, generally speaking, which is something you'll do in the assignment. Color, we don't need so much color because it's not an application you have to. In a lot of machine vision applications, you don't have to worry about color in particular, because a lot of the time you're talking about monochrome being sufficiently accurate to get that measurement data out. Image processing. And of course, processing being a simple example we had to start with was thresholding. There's various types of thresholds you can use. One way of overcoming things like you get quite a lot, especially in the UK, is, for example, is changes in background light. And changes in background light when the clouds go over the sun, and then this can cause tremendous problems. I remember we were developing a system for a company in Salt Lake City some years ago. We had spent ages on it and got it working pretty well. And then we suddenly got, the sun came out in the spring and started shining through the roof onto the thing we were trying to measure certain types of boxes for air freight using a laser triangulation. And suddenly it didn't work, so it went into a spin, and we thought, how can we deal with all these changes in background light? And there's one way of dealing with that in Labview is special types of thresholds that will change depending on various parameters. But I'll tell you a good way of dealing with it is to do image subtraction. And with this, you take it, suppose you've got the laser, you turn the laser off, you can turn them on and off high speed, take an image, and then turn the laser on and take another image. And then you subtract the first image from the second one. And then this gets rid of the background light. And the reason why it's so good is that no matter how much the light's changing, if you do that quite quickly, it will remove the effects of the background light. You'll see the laser line clearly. And that is very good. The only time that wouldn't work, of course, if the light got so bright, the background light, that it overexposed the image, I guess. But other than that, that's a very powerful technique for dealing with changes. Because a lot of the time, we've got, especially something I asked you about in the assignment, is how you would deal with various problems that you might be experiencing, like changes in background light, vibration, temperature changes, even things like dirt, and it's quite common, dirt and muck kicking around in the factory environment. We got a project on in Gloucester with a company, and we're working in a warehouse, and it's not exactly a clean environment in there. And putting cameras into boxes to keep dust and muck off them is quite a serious aspect of the work. Another thing we did with the How's My Cow that I mentioned before is we had it working on a farm. And I was a bit amazed when the farmer said he wants to fire a hose pipe directly at it. So we had to have it completely waterproofed. And of course, if you have it waterproofed, you have to worry about temperature dissipation, heat dissipation, keeping the temperature right. Well, we got it all working, and it's operating around the country now, about some dozens of farms. Filters, I talked a bit about that before, convolution. Morphology operations. Now, basic operations like dilation and erosion I talked about. Fill holes, of course, that's a good one. I mentioned that one. Boundary detection, rejecting the particles in contact with the boundary of the image. And analysis is a nice one because it's particularly good for the assignment, and that particle analysis is a good approach for the VI for working out the area of particles in the image, and not just the area. Also, you can characterize the shape of the particle in various ways, which is kind of useful. You can also use it, for example, to get the area out and then to get rid of very, very small noise in the particle. Ignore any particles that are below 10 pixels in size or something, something like that. That's another way of doing it. Color processing operators. So this is all fairly self-explanatory, and it's definitely worth going through this and having a look-see at what National Instruments' take on this kind of technology is. Now, chapter 2 is getting measurement-ready images. Yeah, so this is a very important part of computer or machine vision. This is a very, very critical aspect, and something that books don't normally talk about much. But getting the camera right kind of sensor, lens, getting the configuration of the camera object set up, and particularly the lighting, the right kind of lighting and operating the light way, is where a lot of the work is in machine vision, to be honest. Because there's no way you can take a second-rate image and turn it into something great. You need to take the best possible image you can, illuminate it with the best possible illumination. Nowadays, LED, most likely. Calibration is a big part, as I mentioned a minute ago. You've got to relate the pixel coordinates to real-world sort of millimeters measurements. I'm at create. Yes. These are different data types you get in Labview. Floating point, for example, for measurements, and integers for simple counting. This is all fairly self-explanatory. There's no point in me going through reading it all out to you. Input and output combinations, image analysis, histogram calculations. We look at the grayscale distribution of the image. Filling, image processing. These connector panes are, of course, ways that you connect the icon or the VI to other VIs, and they appear upon the plot diagram next to the icon. And you assign them, and that's a way to decide how the VI is going to interact and be connected with the outside world, really. Arithmetic and logical operations, read an image, acquire. So when it comes to actually capturing the image, as I mentioned, one way of doing it is snap, and that's the simplest way of doing it. So that's the way we use a lot of time. If you need more sort of precision synchronization, you'd use acquire, and then read file, read data from a file. Display an image, I mentioned a minute ago, with these WinDraw VIs. And that's the color palette, that's the get palette, right, is what you need to use. So you need to use the VI get palette to input into WinDraw to display a given image in the right way. You don't want to try and display a binary image using a grayscale palette, for example, so it will appear completely black, as I think I mentioned before. So you do need to put that in, and that's quite something useful to remember. So one thing you can do a lot of the time with, as I mentioned before probably, is you get the connector tool, the wiring tool, you just click, you just hover over the VI, you should see the connection, you right click, and then you can go to create on the menu that comes up, and you can create a lot of the time controls like inputs, and they will have the right type of data for that input on the VI, and they will save you some work, and that you won't have to necessarily always create inputs or whatever and then wire them, and it will do it for you. It will create the input for you. It's a way of saving time and making sure things work quite well. Image display control, you can play around with all these things. That's what we get. And there's quite a lot of explanation. Attach calibration information, analyze an image, a lot of image analysis. There are a tremendous number of VIs been developed for analyzing images in different types of ways. Line profile, get that pixel distribution along a line in the image, improving an image. You won't need to use all these, but it's worth knowing about them. High pass, low pass filters. Grayscale morphology. Yeah, it's kind of interesting. Morphological. Frequency transformations. I mean, a very common task that's undertaken in machine vision is use a frequency transformation to take an image and then turn it into the frequency domain. Fourier transform has been a common one. Another common one is Hoff transform. You can look these up. Making measurements in the grayscale and color. I'll tell you how to do that there. The toolpath transformations. There's a lot of material here, as you can see. Not all of it we necessarily want to go through in detail, but just thought I'd give it as a bit of background so you know kind of things that we're, National Instruments take on what we're doing. Performing particle analysis. This is kind of a part that might well be useful for the assignment. And threshold, of course, we talked about, and so on. Proving the image. Reject border, I mentioned that one. Yes. Separating touching particles, we've got one there for that. Separation VI. Particle analysis report, nice one. These kind of VIs giving you loads of data, as I say, on the. Sometimes they change these, by the way. They change the exact name and the exact way they present it, but basically they have something very similar to what we're talking about here. Performing machine vision tasks. Stuff you might think is obvious, but sometimes the obvious could be the critical part. Various measurements of parts. This is where back illumination for this kind of task would be good. You put on a light table and then you can see the silhouette and you can measure it quite easily that way. You avoid specular or top highlights, which can sometimes create a problem. Different types of measurement analysis. Pattern matching, algorithms, yes. Yes, loads of detail. I think that's a fuse box in a car that I'm using there as an example. Colour we don't have to worry about so much. Measurements, all sorts of different measurements you can take in various ways. And these are all different VIs for doing analytic geometry measurements. And there's a lot of this stuff. Probably nobody uses all of it, possibly. But reading characters, you've got optical character recognition, of course, built into Labview. And you can also read barcodes. Nowadays, QR codes. And yeah, there's VIs for all this. This is distortion calibration. I mean, calibration to get rid of distortion. I think I talked about this earlier. Calibration template. So they supply these templates which you put in front of the camera to sort of know what it's looking like. I just do quite a lot of work with this myself, templates, especially in 3D systems. They need calibration quite regularly, actually. Real time, there's quite a lot on that. We don't have to worry so much at this time about that. Troubleshooting. Oh, yes, indeed. Programming errors. Different errors that come up. The error control coding is quite good in Labview. It gives you detailed information on what the, rather than just an sort of cryptic error message, it will tell you really where the problem is. Glossary, okay, yes. Tell you what the different terminology means. We'll have a quick glance through this. And there we go. So we got the index. So that's that document. So I've just gone through that. So I hope that's of interest. Now, the PowerPoint introduction to Labview virtual instruments. Also, there's a bit of history background there. So thanks very much. I'll see you next time.